All this while we've been discussing about capacitances, inductance, and the kind of energy stored within electric and magnetic fields. Now let us take a baby step forward and try to define current density, and current continuity equations. Now speaking about current, what first comes to our mind would be a simple circuit where you have a resistor connected to the terminals of a voltage source. Now this would lead to the flow of some current through the circuit. And we obviously understand that this current is going to be dependent on the difference of potential that exists between the terminals of this resistor. So there exists a current due to some potential difference. Now such current which flows due to some potential difference we refer to as drift current. Now if we do have a drift current, we would have an alternative as well. Say for example you had a capacitor connected to the terminals of the voltage source. Now this would lead one plate to be positively charged and the other plate to be negatively charged, leading to the existence of some electric field and some current to flow due to the electric field that exists. We refer to as displacement current. Current, we have two different types: due to potential difference, which we refer to as drift current, and due to the electric field that exists is displacement current. Okay, so we say that 1 ampere of current flows when 1 coulomb charge passes through the surface in 1 second. So imagine a surface with 1 coulomb of current flowing in 1 second. You say that you have 1 ampere of current. With this definition, we can mathematically express the current as the rate of change of charge, expressed in coulombs per second, which we define as amperes. Along with current, we define current density. Now, density of any quantity would be that quantity per unit area, right? Current density is defined as the current through unit surface area, where the surface should be held normal to the direction of current. So as per definition, we can mathematically express that current would be the surface integral of current density, and in turn the current density is going to be volume charge density times the velocity of charge flowing. Having said that, continuity equation is based out of the principle of conservation of charge. Just like the principle of conservation of energy, where energy can neither be created nor destroyed, charge can neither be created nor destroyed. Displacement current density is defined by Maxwell, which helps a lot in proving time-varying fields. Now, time-varying fields being the field generated due to alternating current. And this was later proved experimentally by Hertz. And to prove current continuity equation, let us consider a closed surface with current density J. So the current crossing the surface, as per our definition, is going to be the closed surface integral of J. Now, assuming that the surface has current flowing outwards, the surface would be depleted of charge. Now, the outward flowing depletion of charge being represented by minus dq by dt. So, the outward current is generally going to be minus dq by dt. Now, this expression, that current I being represented as the closed surface integral of J being equal to the negative rate of change of charge is what we refer to as the integral form of continuity equation. Having explained the integral form of continuity equation, let us now try to apply Gauss divergence theorem on this expression here. Now, Gauss divergence theorem states that the closed surface integral of any vector can be represented as the volume integral of the divergence of that vector. Now, making a simple substitution into the integral form of current continuity equation would state that the divergence of current density is going to be the rate of change of charge. Now, having said this, we already know that charge is the volume integral of volume charge density. Now, making this substitution here is going to take us that the divergence of current density would be equal to the negative rate of change of charge density. Now, this can again be written as now this expression, upon comparison, since you have the volume integral on both ends, can be simplified as the divergence of current density being equal to the negative partial differential of volume charge density. This expression is what we refer to as the differential form of continuity equation. More in the series to follow.